Okay, again, so when you do this power up handler, you have the two options here. So here you would go in here and create a program for the power up handler. So you go power up handler, and then create your subroutine, and then go power up routine. Configure the routine as the main routine for the program, and then you're off and running. Okay, next we're going to go ahead and configure the analog cards and setting up PID instructions. So the first thing we need to do is just find out what a PID instruction is. And they have classes in electrical engineering on this, and they're controls classes. But basically what a PID instruction does is it takes a set point, and then it takes a measured feedback, and if it's closed loop, and then it controls something. So here, let's say that this is your summing junction. That's what they call this right here. And here's your set point. Let's say the set point is 1. And then you've got your error, and let's say their feedback is 0. So you'd have an error of 1. And then the PID resides here. This would be your proportional integral derivative controller. It decides what the controller is going to do. It's the decision maker. It makes a change. It does a control action. It manipulates the control variable, or U. This is called U right here. This is called E, the error. This is the control variable. And then it does something. It fills the tank. Let's say if this is a control valve or something like that, it actually starts opening up the control valve if the tank needs to fill, or closing the control valve if the tank needs to empty. And then you've got closed loop feedback here, and this is measuring the tank level in this example. It comes back here and it says, okay, now I'm 0.5. So it says this is a 1 and this is a 0.5, so we have an error of 0.5. So again, the PID decides and makes a change, and decides how fast to make a change. So, you know, what you see here is you see a rise to your set point, then it comes down, slightly goes below your set point, and starts settling down on your set point and stays right there on your set point. So this will continue to go back and forth until the set point is equal to the measured value, or more importantly, the measured value is equal to the set point, because if these are equal, then error is 0, and then the PID just says, okay, I'm good. I'm exactly where I need to be. I won't make any more changes. And that might be 50-60% of the valve position. It might be 50% open or something like that, or 60% open. And then you're just sitting there modulating slightly, opening and closing. If there's any disruptions in the plant, such as a user all of a sudden just starts really using a lot of water and it starts dropping the tank level, then all of a sudden the measure will say, hey, wait a second, we're supposed to be at 75% tank level and we're down to 60%. So we have an error of 10. So we're going to open the valve more to fill the tank up more to compensate for this change in usage in this case. So if the usage is dropped, so the tank would start filling back up, right? So it'd start increasing in level, and that would come back here and say, oh, no, wait, I'm above the set point now. So now I've got to go, this becomes a negative error, and then this guy says, okay, let's change this and start closing the valve so the tank drops down, and decreases back down to your desired set point level. So here we actually have a pictorial example of this. This is really controls, and this whole controls idea. If you take that FE EIT exam, you're going to have to do this a little bit more, and you probably have to take one of the quick courses that I offer on controls, because it goes into a lot more detail than anybody that's learning PLCs would want to go into. But this is just a basic idea, and every PID or every PLC instruction programmer needs to understand the basic PID instruction. Now you can actually have a PID and then after it another PID, and that's kind of like a cascaded control PID. So you have a PID feeding the output of a PID, feeding the input of another PID, and then that output goes to the actual control variable, and then it comes back around and feeds back on itself. And you can really get fancy with these different PIDs instructions. So going back to our example here we have an on-off valve. Whenever this valve is open, then the tank just fills up, right? And then the idea is to pump the tank empty right here, just to let it out. And if this valve is fully open and this pump is just on all the time, it doesn't have a variable frequency drive on it or anything like that. It's just wide open. A variable frequency drive actually varies the speed of the pump. So you can actually vary the frequency of the pump, and that's another one of those short courses, the VFD course. So the pump is, in this case, it's just on-off. It's wide open. So we modulate this valve fully open or fully closed. If we modulate the valve fully open, the pump is strong enough to push that water out so fast that it'll drain this tank. And ideally, when this valve is on, there's enough water coming in to fill the tank. So, but there's not too much water going in, and there's not too much water coming out. So the modulating valve takes care of that. Next, you have a measuring element. This is a level indicating transmitter. And usually they have a number associated with them because you might have multiple level indicating transmitters. And because this is on the bottom of the tank, it's actually a pressure transmitter. So it actually looks at the pressure of the column of the fluid. And you can study this on your own. I'm not going to go over how the physics works of that. But anyway, it's a level indicating transmitter that sends you a 4 to 20 milliamp signal back to an analog input card. So when you look at this whole PID instruction, you should be able to say, okay, I have a digital output. If I have some limit switches, I have at least 2 digital inputs. I have a tank, I have a level transmitter, so I have an analog input. I have a pump, so I probably have a motor starter. I have at least 1 output and 1 input to tell me if the motor starter actually started or not. And then if I have a modulating valve, I at least have 1 analog output, and I'd like to know the position of that valve, so I do 1 analog input. So you can actually look at a diagram like this, and in your mind you can say, okay, I know what I need to build this PLC program or build this PLC control panel. So again, let's convert that into our set point, our desired tank level. We have our error, we have the PID to controller, and here we have the modulating valve. That's the control variable actually is controlling the modulating valve, right? Because it's opening and closing the modulating valve. And then comes around here and goes back to the level indicating transmitter, and then back to your error. So this is your summing junction. This is positive, negative, and this is your error, your PID, your K, your gain, your integral, and your derivative values, and your loop update time, and your min and max value, because you can limit the output here on the action. Okay, so that's actually this tank now put into a PID diagram. And you can see this is a closed loop feedback, and that's how we'd have that. So we've closed the loop. See how we're closing the loop. The measurement point is actually controlling the modulating valve. Now, in reality, you'd say, oh, wait a second, why don't I just tie the level indicating transmitter to the modulating valve? Well, that's not going to work. You actually need to have a controller in here. But you'll see a lot of process engineers, they just kind of dot over here and point to the modulating valve, and that tells the processor, the PLC programmer, that, hey, these guys want me to modulate that valve based off tank level. If they had a flow transmitter here, an FIT, and they pointed this to that modulating valve, then that would tell the operator or the PLC programmer, hey, they want me to control the flow with that modulating valve, which is entirely possible. I don't know why you'd put it on the suction side of a pump. That wouldn't be a good idea. You'd want to put it on the outlet side, but neither here nor there. You could have it even here if you wanted, I guess. So next, we'll look at the actual instruction. The PID closed loop control holds a process variable at a desired set point. The following figure shows a flow rate fluid level example. So here they have, there's X number of flow coming into this tank. They have a level detector, and then they're coming out of here, and they have a modulating valve. So they're opening and closing the modulating valve, and they're putting this in terms of how the RS Logix 5000 and 500 wants to see it. They want to see a process variable. This is the process variable, the feedback, your set point, your error, And so you can see here they went negative positive, and you can actually reverse this relationship. And then coming out of here, you go to your PID equation, and then coming out of here is your control variable, right? Your CV, your control variable that actually modulates the valve. So if you feel so inclined, you can study this formula, and the way you get to this formula is you actually go to your help, type in a PID instruction and go to your help screen, and you can actually look through there and study this. So the derivative of error, so they actually give you the equation for that, and the process variable is E, your error, minus your set point, minus your process variable, and your control variable equals Kc times E plus 1 divided by T, the integral of T to, the two limits, T to 0, E, the change of T minus Td, and you've got the derivative, dPV divided by dt, so this is the derivative of the process variable plus the bias. And then if you have E equals PV minus SP, remember right here I said this is minus plus, this could be plus minus, right? So here's set point minus process variable. Set point, see this is process variable coming in here, process variable minus set point. Or process variable, you got set point minus process variable, or process variable minus set point. If you change the controller to this, you're actually changing this right here. So you can see it's the same formula, but you've changed your process variable with your PE here, right? If you go independent gains, you have your process variable PV equals E, the error equals set point minus process variable. And then here you've got error, E, CV, control variable equals KP. KP is the gain times the error plus KI. KI is the integral value. And then you've got your integration here. And then you've got your error. So you're taking the integral of your error, multiplying it times your KI, your value KI, plus KD. KD is your derivative. So if you have a PID, right, that's what this is. K is gain, constant. KP is your gain, your proportional value, times your error, plus KI times the integral of your error, plus KD, which is the derivative of your error, plus your bias. That's how you read that. Now, and some of you guys are thinking, good God, I've never taken calculus. I don't need to know this, do I? You don't. You don't need to know it at all. It's not relevant in this. I mean, it is relevant, but for most level control valve situations or process control valve situations, you don't need to know this. And I'll show you how to tune a loop. It's pretty straightforward, actually. Unless you get into some complicated loop that has a super long delay. We were trying to control an injection on a process, and you would inject this chemical, and then 20 minutes later you would see a change. That's a long delay. And usually these loop update times on these controllers are 10 seconds. So the processor, the Allen Bradley processor would say, okay, turn on, right? Make a change. And then it checked 10 seconds later and say, hey, you didn't increase. Increase. And it would increase, the more chemicals would be dumped into the solution. And then finally, 20 minutes later, it'd say, hey, wait a second, you've got too much chemicals. So the controller would say, okay, well, I'm going to come all the way down to 0. So this thing would go on, then off, on, then off. So the loop update time in the entire process needs to be fully understood before you implement one of these PID instructions. But typically, if your valve, your control variable, right, if you go from 0 to 100% and it changes states within 3 seconds, you can control this thing like no problem at all. And if your process is designed right, you've got the right amount of flow coming in and the right amount of flow coming out, and the control variable, in this case the modulating valve, is about 75% open, and that's about a perfect balance for this system, then you should be able to control not all upsets, but certain disruptions in the system that are not outside of the realm. Like if you shut off the inlet of the water, you're definitely not going to be able to control that, right? You're going to go start looking at that tank level and say, no, I got alarms, I've got some shutdowns, and etc. We'll cover that later in the ISA section. So again, if I say I have a P controller, all I have is a proportional controller. What I've done is I've set the Ki and the Kd to 0 because, or very, very close to 0, right? So if I put Ki to 0, 0 times this value, anything times 0 is 0, right? So if I put Kd to 0, anything times Kd, or 0, is 0. So taking the derivative of the error times 0 is still 0. Taking the integral of the error times 0 is still 0, and you're left with your Kp times your error. So you can have a fully proportional controller, and it's real simple. All you do is say, okay, I want a proportional controller, and you just set I and D to 0, and you've got a proportional controller. Now you can also, and you can say, well, gosh, why do I need a PID for this routine? And you're right, you could actually mathematically solve this and create a type of, a ramp up type deal. But the PID is so easy to use that it just makes sense to use it, Now, if you wanted a PI controller, you would just set your D to 0, your derivative, right? So you get the idea how this actually works. I'm not trying to tell you to solve the integration of the error or make a complex instruction or anything like that, or go study calculus and learn controls. It's not necessary. You don't need to do any of that. All you need to do is drop the PID instruction in there, know what your proper process variable is, know your control variable, and make sure that you can walk up to it manually, open the valve to 50, 60%, and see that the system is somewhat stable in this case, right? Then you know that your process variable, your process engineers have designed, or maybe you're designing it, you've actually designed the proper flow in, the proper flow out, you've got the right size pump. Because if you've got too big of a pump and you turn that pump on and you crack that valve open and shoo, all the water comes rushing out of there much faster than you can put the water into the tank, you're never going to control it, right? You're going to slam that control valve shut and deadhead that pump and destroy the centrifugal pump. So then you would actually have to have a loop around the pump, which is not a bad idea anyway, just to keep it from deadheading, but that's a whole nother story. So again, these variables, the Kp is a proportional gain. It's unitless. It has no, it doesn't have a dimension like seconds, or it doesn't have a dimension like millimeters or anything like that. It's just a value. Ki is the integral gain. It's in seconds. To convert between Ki integral gain and Ti, you sometimes hear it's reset. Ki, the integral, is the reset. So to do that, to convert that, you just simply take the Kc, which is up here, divided by 60 times Ti, and that equals Ki, your integral gain. Here you've got your derivative gain, and then you can convert between Kd, the derivative gain, and Td, the time rate, right? So here Kc is a controller gain, and then you have your Ti, your reset time. Td is your rate time in minutes. SP is your set point. PV is your process variable. E is your error, and it's based off of SP minus PV, your set point minus your process variable, or your process variable minus your set point. And then your bias is your feed forward or bias condition. And then your control variable is your control variable, what you're sending out of the PID. And then you've got your loop update time, right, DT. So again, here's what a proportional integral derivative, or PID, instruction looks like, and you can see it's proportional integral derivative. And you've got your actual PID value, process variable, PV data type, tieback, control variable, CV data type, PID master loop, end hold bit, end hold value, set point, process variable, and output percent. Some processes are just so hard to understand or to control. There are engineers that do nothing but focus on control loops. In fact, one of the exams, when you go up for an electrical and engineering exam for your Texas license, you can be a PE, right, a professional engineer. You can decide, well, I want to take it in power, or I want to take it in controls, right? Because controls is such a big subject that you can actually take it in controls, and I think you can even take it in computer science or computer and controls type thing. Kind of like leaves some of the guys that have gone through the newer schools, and or I guess they're graduated in the last 5 years or so, and they've learned a lot of PC, programming, stuff like that. And so when they go in there to take that exam, they're like, oh my God, look at all this control stuff I have to take along with my computer science, and it's real tough for them. So you can actually, people actually do nothing but controls, and that's what you're kind of doing when you're a PLC programmer. You're a control guy, right? You're a control engineer. So again, here's your breakdown, and you can get this in the help menu. So your process variable can be an S integer, an integer, a D integer, or a real value. This is the value you want to control. I want to control the process variable. The tieback, it's optional. I never put the tieback in there. The output of the hardware hand auto station, which is bypassing the output of the controller. Enter a 0 if you want to use this parameter. If you don't want to use this parameter, and I always put a 0 in there. Because usually what I do is which you'll see in a second, I'll actually go over one of the way I do it. And there's different ways to do it. There's no right way, no wrong way, unless you go out, unless you fault the processor, which you don't want to do that. But I actually set a hand and an auto mode or a manual auto mode. And when I put it in manual mode, I just write directly to the output and don't even turn the PID controller on at all. But some people like a bumpless type control. I rarely ever do that, because if you put anything in manual, in my mind, I do such localized or process dependent offshore skids that anything in manual messes up the entire process, and you got to shut the whole system down. So anything that goes into manual, I just shut it all down, especially a PID that's controlling a flow or something like that. You don't want to have that in manual mode. But some people want to go from manual to auto bumpless, and so they'll use these tieback values. Your control variable is the value which goes to the final control device, the valve, the damper, the VFD, the variable frequency drive, etc. If you're using the deadband, the control variable must be real, or it will be forced to 0 when the error is within the deadband. So you don't want to do that. You don't want to be cruising along at about 75% of the value, and all of a sudden you have a deadband and you're not real, and all of a sudden the controller just goes to 0. That would be a problem. You'd be scratching your head trying to figure out why this thing's not working. You'd watch it, it would be working. The minute it got within your deadband, it'd go to 0 again. So usually what I do on PID instructions is that I just make everything real. Then you've got your PID master loop, the actual instruction itself. And if you are performing cascade control, again, cascade control is when you put a PID in front of a PID, and then you've got some type of a slave loop. And this PID is a slave loop. Enter the name of the master PID, enter 0 if you don't want to use this parameter. Okay, so then we have the in-hold bit, and this is optional, and I never use it. Current status of the in-hold bit from a 1756 analog output channel is to support the bumpless restart. So if you wanted a bumpless restart, you would actually look into the in-hold bit. So here we have the in-hold bit again, and the set point. This is for display only. You cannot manipulate this value. You can manipulate it outside of the controller and move a value into the set point, which I'll show you how to do that. And then you got your process variable. But when you look at the actual instruction here, you can't just go in here and type in. You can't go in here and type in a value. You can click here and open it up, which will show you how that happens, and you can actually type in a new set point. And then you got your process variable, and you can actually see it's display only, and the output %output, it's current output percentage value, and it's for output display only as well. And then you've got your different bits, your enable bit, and if you wanted to look at some of these values, you could. And then it breaks down so let's say you called your PID instruction the tag, you called it PID1. So your set point would actually be PID.SP. So if you had an OIT man-machine interface or one-to-ware or an HMI type system, and you had an operator type in a PID value, they would take that value and do a move command into the PID1.SP, right? And so that would actually move that variable into this instruction. The KP, again, is the gain, right? It's a controller gain, and it's a proportional gain if it's independent or dependent. And you've got your KI as a real value, and its KI is your independent gain. And again, this is your integral gain. And again, you can actually say, if you made your tag name PID1, it would be PID1.KI, right? And that would be your integral value. Then you've got your KD, real value, your bias, your max S, the min S, and then you've got your dB. The max S and the min S, actually, those values, I don't think you can actually change, but you can change the max O, min O. And what these are is you can actually put a limit on the output. You've got to check a little box to make sure that you can do this. And you can say, okay, I don't want the control variable to ever open up more than 90%, because I know when I'm at 100%, I can't control this thing anyway. So I don't want that condition to happen. So I limit it to 90%. And I don't ever want that control valve to close all the way, because if I do that, then I'm going to deadhead the pump and destroy the pump. So we don't want that to happen. So you set max O to 90% and min O to 10%. And then no matter what your controller tells it to do, it's going to be within that range. So on real hard things to control, where the loop update time is just way out there, right or wrong, I'll set this max min limit pretty tight and let the controller kind of control within that limit. It's kind of really hindering the PID instruction, and it's really a bad application. So you want to make sure that you open this up wide enough so that you can have some control. Now, if you take min O and make it larger than max O, then you're going to fault O. You'll fault the PID instruction. So you got to make sure that doesn't happen. You have to actually put in something to do that. And then you've got your .UPD, the loop update, and this is how fast it updates in time. Now, if you do the loop update, what you need to do is you're going to need to make sure, let's see here, that you have the loop update, that you're in a time mode. Oh, I guess that's actually in PI. The other Ars Logix 5000 or 500 actually has the timed and SBC mode. Okay, so anyway, then you've got your process variables. You can actually program some process variables and alarm on them. And you can say, hey, wait a second, I've got a high alarm or I've got a low alarm, and you can do derivative, a deviation alarm limit, positive and negative, and a process variable alarm deadband. And here we've got PVDB, which is your process variable alarm deadband, and DVDB is your deviation alarm deadband. And then you got your maxi and your mini value, with your maximum process variable value, minimum process variable value, your tie back for manual control, and then you've got your max CV control variable, right? Your maximum control variable value, minimum control variable value, and it'll correspond to 100% to 0%. Your minimum tie back value for your manual mode, and your max tie back value for your manual mode. And then you've got your actual data, real. So I'm not going to go through every one of these, but you can certainly go ahead and go to your help menu and actually read through every single one of these. But if you look right here, let's just look at how you could do this in manual mode. You set the .mo, so it would be PID1.mo. If you turn that bit on, you'll be in manual mode. If you turn it off, you'll be in automatic mode. You can actually allow the operator to change this value, PID1.PE, and that'll change the PID equation from independent to dependent. And you recall, when we were looking up in these formulas here, let's go back up there real quick. You can see you have, there should be an independent and a dependent. Here's an independent gain right here. That's what they're talking about there. And then you can do no derivative smoothing, or you can do, you can filter it. You can do a derivative smoothing filter, disabled or enable it. And you can go through these different points. And these are actually Boolean values. These are all real values. These are Boolean values that are on, off, 1 or 0. Okay, so the PID instruction typically receives the process variable from an analog input module and modulates the control variable output, CV, on an analog output module in order to maintain the process variable at the desired set point. So again, your process variable is an analog input card, or input, to one of the cards. So if you have the 1756 IF16 module, and you put it in differential mode, you've got 8 analog inputs. So if you have one process variable, then you have used up one of your analog inputs. And then the control variable uses one output as a minimum. And if you'd like to know what the valve's position is, like position feedback, you would have another input. So you'd use 2 of your 8 available. The .en bit indicates execution status. The .en bit is set when the run condition transitions from false to true. The .en bit is cleared when the run condition condition becomes false. The PID instruction does not use a .done bit. The PID instruction executes every scan as long as the condition is in a true condition. So you can see here, this is your rung state, and if it's the .en will turn on as long as the instruction is allowed to turn on. Okay, so here's an actual example. And you've got level control valve modulation OK. So whenever this bit turns on, you're going to allow this thing to control, right? And so you've got PID, level control valve, PID. It's a tag, right? It's a real value. Process variable, level control value underscore PID underscore PV, process variable. And these can be any names you want as long as they stay within the tag convention. Again, I said tieback is 0, so I'm not doing this manually. I don't use that feature. You can certainly use it, though, whatever you feel comfortable with. The control variable here is the level control valve PID control variable. PID master loop is 0, and hold bit is 0, and hold value is 0. Set point here says 2.484, right? 3109. And you can't change these values, right? You can't manipulate these. These are the results. Now you can manipulate the set point right here. If you go and click that tag right there, you'll get the view tag configuration dialog. And what that looks like is here you've got the tuning tab, the configuration tab, the alarms tab, the scaling tab, and the tag. So set point is right here, and you can actually increase and decrease it. See these little arrows right here? These are the values you can change. Your set output, your output bias, your tuning constants, proportional gain, KP is 5, integral gain here, KI is 2.5, derivative time is 2. So if you wanted a proportional controller, you would go ahead and set this to 0 and this one to 0, and you'd leave this to some value greater than 0, and you'd have a proportional controller only. And remember the formula on that was KP times E, the error. So if you set this to a little integral here, you'd have a PI controller. PI controllers are good for a lot of things, actually. Speed control for like generators and what have you. They can be used for flow control valves, controlling the flow in a process, or even a level control valve for a tank. PIs are actually a lot easier to use. And the way you would tune this, the easiest way to do this is once you've manually made sure everything flows properly, right? You know that you've got enough water coming into the tank, and you know that given the valve position at 75% open and the tank run and the pump running, that everything's kind of stable. It's neither increasing real fast or decreasing real fast. It's kind of stable. So now you know you can actually control it. So if you were careful at that point, you could actually open your output valve manually a little bit more, or close it a little bit more, and find that magic number where it's completely stable without any disturbances, right? At that point in time, you could actually see some stability. If you know that happens, then you know you've got a stable situation. And then what you would do is go into automatic mode, start the unit up, the pump would start, the inlet valve would open, and the tank would start, the valve would start modulating open and closed. And you would set your D to 0 and your I to 0, and you'd start increasing your KP. Increase your KP until your the output valve starts to move, right? It's just going back and forth, open and closed, right? Once you find that value, whatever that value may be, cut it in half. Let's say that value is 10. At 10, this valve opens and closes. It modulates, right? It's cycling. Cut the value to 5. Just cut 10 divided by 2 becomes 5. Then take your integral and add half of the proportional gain. And if you do that, you'll find out that your process usually tunes at that point. And then down here at the bottom, you can actually see your set point, your process variable, and your error, right? You can see that your output is open 40%, your tieback is 0%, and your mode is in auto mode, so it's actually in auto mode. You have a process variable alarm, high, deviation alarm, low, output limiting, low, error within deadband, no. So that means that this is too great. Maybe deadband is set at 0. You know, if it's set at 0, well then you're gonna get this. It's not gonna say it's okay. You can actually use this information and send it back to the DCS and say, hey, you know, your deadband, you're not within your error. You've got a problem you can't control. Set point out of range. You can actually set a range for this, and you can say PID initialized, yes. Okay, so what I do is I have the first line of code here is I say, okay, I have an OK bit, and it says OK to modulate the valve, right? So that means everything's in auto, right? I have no shutdowns. I've actually started the system. I opened the inlet valve. I started the pump, and I'm ready for this modulating valve to do something. I want it to go to its min position and then start modulating. If I put it in manual mode, that would be just in this case, you can actually rock it. So it's in manual. So unlatch your auto. If you're in auto, unlatch your manual. And so if you're in manual mode, then send a value. Here we have LCV, level control valve in manual, and it's got an alias N101 in brackets 39. So when I put N10139, I can actually have something remote, a remote computer or a remote OIT actually control this value, and the operator would type in a number from between 0 and 100%. So if it is in manual mode and they type in 100%, it'll automatically move the output valve, the control variable, to 100% position. And you can see that here. If it's not in manual and it's not okay to modulate, I want to go ahead and just close the valve. Some people don't want to close the valve, right? In this case, I say, oh well, send a 0 to the level control valve manual, so that the operator always has to increase the value again, and then also take that 0 and put it in the output card right here. You can see I put a 0 in the output card. So in its local slot 8 output channel 2, right? And I move a 0 into there. And then if I am in manual mode and it's okay, you know, I'm got a valid signal up here. I'm within that range. It's greater than or less than it's greater than 0, less than 100. That's a valid signal, so I say it's okay. It's a good value. And why would I even say that? Well, I do it because you don't know if OIT is going to squirrel out on you and give you some bogus value. And this prevents you from sending that PID a signal that it shouldn't have, and would cause your processor to fault. Because if your processor faults, your operator at that point has to turn it off, turn it back on, and hopefully it comes out of that fault condition, or rock that on-off the key switch from program, from run to program back to run, and hopefully it clears there. And if that doesn't clear and you've got a bad value in that PID and you can't get it out, you can decide at that point to do some type of fault handling, or you have to go out there and fix it. Or if you've got an L61, you can give them a flash card and get back up and running that way as well. So I don't take any chances, and I validate all the inputs, all the values coming in. So if this is it's not in manual, not okay to run, I put a 0 in the manual valve position, and I send the valve closed. If it is in manual, I just take that, whatever value they give me, 0 to 100%, and I just throw it in the output card. And then, of course, I've got the output card scale for 0 to 100% in this case. Okay, so next thing I do is I have a divide. And the reason I divide here is I just want to go ahead and get this value into a proper, you know, let's say if the input card comes in and it's a different unit, or if there's some division I need to do, I'll just go ahead and do it here. A lot of times I just put 1 here, and it does nothing. All it does is just takes that value and sticks it into level control process variable. So this is actually the tank level, right? The actual level control valve in this case, and I multiply it times 100 and put it into the process variable. Next, I actually take the KP value in 101 and 10, and it's from the OIT. The OIT is the Operator Interface Terminal. By the way, some of the next courses I've been asked to do are the RSView Studio, RSView 32, Panel Builder 32, Quick Designer. Those are all OITs and things that you can connect your PLCs to. And I'll do that. I'll actually go through those. Those might take me some time to do it, but I will do it. So keep an eye on that as well. Let's see, and then we have our KI from the OIT, and we put that in our LCV PID.KI. So if you slide down here, you'll see that the name of my PID controller is LCV_PID, right? So that's why I'm moving values into LCV_PID.KP. If I called it just PID, it would be PID.KP, right? So I actually take these values and drop them in here. Now, if I really wanted to be careful about this, I would do data validation on these values as well. And then here's your KI, your KD, your loop update time, your deadband, right? You've got a deadband. What you're doing is you're allowing the operator to adjust these values so that they can tune their loop. And why you want to do this is because if you've got this on your factory floor, you don't have what they have. You don't have the same values, the same process, right? Things change. So you want to give them the ability to tune these loops. Okay, so here's you've got your max O and your min O. That's the maximum value the control variable can go to, and your minimum value the control variable can go to. And then you've got your error. And then what I'm doing here is I'm actually taking the PID.ERR value and putting it in a value called LCV PID_error_OIT, and I actually display that on the OIT. And then I take the output the same way, the actual raw output, and I throw it on the OIT as well, so that they can see their error and they can see their actual PID level control valve's output position and know what this thing's doing. Next, I take if PID min O is less than 0, that's not a good thing, right? We're going to move a 0 into it. If it's greater than 100, we're going to move a 100 into it. Oops. And then we have our PID level control valve PID max O. If it's greater than 99%, then we'll move a 99% in there. Okay. So next we have the level control valve PID max O. If it's, we'll move that value into this PID max O. And the reason I did that is just so I could see it, right? A lot of times I'll do that. If PID max O is greater than 0, is less than 0, then we move a 0 into it. So we're doing the data validation. And then we say if PID max O is greater than 100, we'll move a 100 into it. So we make sure that it's within 0 to 100%. And then we do the same thing. So we did do validation, data validation on all these variables, right? So that way I know that under no circumstances can this PID instruction run if the values .kp is outside of 0 and 99.9, and the min O and max O values are outside of that range as well. Okay, so I'm actually doing all the data validation on the KI here as well, the KD, and the loop update. Because if these values fall outside of these ranges, and then what I'll do is I'll actually go through and type in the min and the max values on all the OITs inputs to make sure that I can't fault this processor. And as long as I can't fault the processor, neither can the operator, right? There's nothing invalid that's coming in. Even if the OIT was programmed wrong or somebody got in there and started playing with it and they were able to change the min and max value that the OIT could enter in, the PLC would have the last level of correction or data validation and say, no, we're not going to allow that. We're going to move it back to the proper value. So here we have our deadband. We do the data validation for deadband as well. And then we have our set point. And we say, okay, now if that set point's less than 0, let's move a 0 into it. If that set point's greater than, in this case, 1,000, then we'll move a 1,000 into it as well. Next, we said that if that min value, the min control variable value, is greater than the max control variable, if that condition occurs, this processor guaranteed will fault in a real condition. The emulator's kind of screwy because it won't let me fault it. But reality is, and that's another reason why you don't want to use simulation or emulators, you actually want to use real I/O. So I know talking to some of the people, they've been watching eBay, and every once in a while a card or a rack or something will pop up at a reasonable price, and they'll go ahead and purchase it. And then with that, they'll get a starter kit, starter software kit from Allen Bradley, a full online version of software, and download into that processor and play with it. That's excellent. If you can get a hold of a Logix 1200 with an analog input card and an analog output card, and then you get your starter kit for Logix 500, you can actually create different PID instructions and control different things and learn a lot about this. And the key to this is practice. You've got to get out there and program jobs, real jobs, even if you have to make them up. You've got to practice. Once you've practiced and you've written some code and you've actually understood it and you've faulted a few processors and you've got them back up and running and you've created different situations with OITs, you're going to get a job. You're going to get a job doing PLC programming. And I can tell you right now, a PLC programmer without a degree can make at least $50,000 a year. That might not seem a lot to some of the people out there, especially in the oil and gas industry, but it's not bad money for a non-degreed professional. And you are a professional if you're a PLC programmer. So take this serious and take your time and really study it. Spend 20 to 30 days working with this program and working with this, these different techniques that I've shown you in courses 1, 2, and 3. And if you haven't already done it, go get the Logix 500 courses. Watch them all. Educate yourself. Work through it. Spend the 30 days. Go find yourself a PLC Allen Bradley 1200 online, on eBay. Somebody's selling one, I guarantee it. There's smaller versions. Another thing, and this is really good idea, call a vendor. Okay, like one of your Allen Bradley vendors or somebody that sells Rockwell software, and say, hey, can I borrow a PLC just for, I just want to play with it, show it to my boss, things like that. And they'll give you a demo, and they'll say, okay, you've got this demo for a month, and you can play with it for a month. I guarantee they'll do it because they want to see you learn how to use that processor. And once you learn how to use that processor, you're going to want to use it. You're going to want to put it in your applications because it makes your life a lot easier than the old relay logic designs. So you want to do that as well. Okay, so go back to the PID. So here we've dropped in the PID instruction. So if the level control valve modulation is okay and all the data validation is okay, this thing should run and it'll actually control that process. And again, the objective here is what? For the process variable to equal the set point. And if the process variable equals the set point, you can see they're not equal right here, then the output will open or close depending on the control action, and it will try and correct that so that these two values are equal. Okay, so next I say if I'm not in manual and I have an OK to modulate, then take the control variable, the output of this PID loop, and throw it to that analog output card. Send it to the real world. Open that valve. Close that valve. Okay? Okay, so here we actually went over this in Logix 5000 number 2, and we actually configured the analog alarms and stuff like that. So you can actually go into here, and this is actually local 7. This is local rack slot 7. It's a 1756 IF16 card, and it's got a revision 1.1. Channel 1, remember when we slid up here, and what did we say our process variable was? We said it was local 7 input channel 1, right? So when you slide in here, you can see that you need to set this guy up. Now this one's actually set up for kind of a goofy, it's not a 0 to 100% condition, but that's neither here nor there. You know, this is a high value. It gives you a process alarm high. A high is 55, a low is 20, and a low is 18. And if you click this, it'll disable those alarms. Okay, so you don't want to do that. So you want to make sure that you are set up on your actual input card. And then on your output card, right here, you want to make sure, remember it says 1 here, so let's check that out. It says channel 2 here, so I didn't do the right one. I didn't display the right one, but you'll get the idea when we go through it. So we should have hit 2 here and said 20 milliamps equals 100 and 4 milliamps equals 0. So if the valve gets 20 milliamps, then the valve will fully open. If the valve gets 4 milliamps, then the valve will fully close. If the valve, if the input here sees something greater than or less than 20 milliamps, greater than 20 milliamps, less than 4 milliamps, and that's out of range, and we want to deal with that as well. Okay. So now let's actually go and look at an example, and we'll kind of try to tune it. I don't have it tied to anything, so all it's going to do is ramp all the way up and ramp all the way down. Actually, I think one of the courses I keep getting pestered to do is the variable frequency class. And with a VFD controlling a fan and then taking a damper and allowing the fan to push the damper open and close the damper, you can tie the damper to a rheostat, a variable resistor, and actually bring that into the input of your PLC, convert that resistor value, the variable resistor value, into a 4 to 20 milliamp signal, and actually control that fan speed so that you control the damper and you can control the airflow. So that's what I've been asked to do, and I honestly just haven't had a chance yet. Okay, so what we've got here is we've created a program with the emulator again. It's called tester and PID.ACD. So if you go here to control, let's slide up here, go to control tester, right mouse click, you can go to properties, and you can see the name of the program is tester. I've got it set up for a controller, emulator Logix 5000 controller, revision 13.26. And here we talked about faults, but you can actually go to this fault window and you can look at the different faults. Let's slide this over so that you know where to go. And you can also go to major faults here. So again, let's cancel this. Let's go back to that. You go controller, right mouse click, properties. Over here you can see the general, you can see the serial set point, system protocol, user protocol, major faults, the memory, let's see here, we'd already did that, minor faults, advanced, you can see controller fault handler, none, power handler, power up handler, none. So, and then security, and then it gives you your time over your slice time. So you can see all these things. And if you do this, you can actually, you'll see if you actually add a controller fault handler, you'd have a value in here. And if you added a power up handler, you'd have a value in there. Okay, so what I've done is I've created a value called process variable. It's got 30 in it, and it just moves to itself 30. And the reason I did it is so you could see it. And then I went down here and I said, here's set point. So you can see that my PID, program proportional integral derivative, is called PID. So PID.setPoint right here. Okay. So now if I double click on this, I can see the tuning, right? It says set point equals 31. So if I go in here and change this to 30.99 and apply it, there it is, it changed. So you can actually change this. Now you see what's happening. When I do that, what's happening is this controller is trying to control, right? It's saying, hey, wait a second. The process variable doesn't equal the set point. So let's do something. Let's move the output one way or another. And it's maximizing. And why is it going fully open? Why isn't it going fully closed? And that really is based off of your configuration, right? So you've got independent versus dependent. You can put dependent there or independent. Control action, that's set point minus process variable, right? My set point is here, 30.865, and my process variable PV is 30. So it says your control action is going to say set point minus process variable, and we're going to do a derivative of PV. Loop update is 0.01. You've got control variable high limit 100%. Control variable low limit 0%. So let's change that. Let's change that to, let's do something drastic, 50. And hit enter and say apply. And so it instantly changed this to 50, the actual control variable. So, and then here's 100%. Apply. So you can actually change these PID settings. And if this was a loop that you didn't want anybody to mess with, only you could mess with it, okay? If you wanted that condition, you could actually do that here and just leave it only in the PLC program. And so whenever you went online, you could tune it, okay? And you could actually do different things like that. And then here's your alarms. I don't have any alarms here, but if you wanted to, you could put process variable high, low, your dead band, if you've got a variable dead band, positive deviation, negative deviation, and a deviation to the dead band. You could actually add these values, and if any of these conditions occurred and you knew in your heart that, hey, these are problems, if this occurs, you can alarm on them and get an operator out there to see what's going on. And then here's your scaling, and so here you've got unscaled value 4095. The engineering unit's 4095, and your control variable is 100 to 0, and your tieback is 100 to 0. And I didn't use the control of the tieback here. And then your PID is initialized. And then you got your tag. Remember, I called it PID. I could have called it anything I wanted to. And then that's it. So now let's play with this a little bit. What we want to do is we want to change these variables so that we see this output change. And so what we're going to do is we're going to say, let's change our process variable. Let's close this, cancel. And we'll change this to 10. All right, so let's see. All right, let's change that to 50, or 60 rather. So now it says, when I changed it to 60, it wants to move. It wants to close the valve because now my process variable is greater than my set point. So it's trying to compensate for that. You can see it's actually closing the valve. And you can see right here it says process variable 60, and you can see set point up here is 30. So it'll just go all the way down to a closed position and stop. Now if we don't want that to close because we don't want to deadhead the pump, what do? We double click here, or we can do it the way I showed you earlier with all the data validation and stuff like that. And we go in here and we want to say configuration, and we say, I don't want that to close. I want this to go to 10%. Apply it. And I don't want this valve to fully open. I only want it to go to 90%. Enter. Apply. Say OK. Now it's 10%. So the PID routine said close the valve, right? But you're limiting the valve to 10% so that you don't deadhead the pump. So if we change this to something below 30.865, let's call it 30 even. And then it instantly jumped to 80%. I mean, it moved fast, right? So let's change that. Let's change how fast it moves. Okay, let's try that. So let's go over here and say this is 1. And let's change this to 0. And let's change this to 0. Now we have what? A proportional gain, right? That's all we have is proportional. Now we also want to go over here and change our loop update time, and we'll change this to 10 seconds, let's say. Apply that, say OK. So now let's see how this thing operates. So here our process variable is 30. Our set point is 31. So we're going to change this to 32. Let's see how fast this thing moves. It's not moving very fast, is it? Let's go look at it. See what it's doing. It's just sitting there. And why is it sitting there? Well, it's going to only check every, what, 10 seconds or so? So let's change that. We don't want to wait that long, do we? Let's change it every second. Apply it. Okay. See if we can get it to change now. Still nothing. Let's change that to 20. Let's increase this. Let's get this thing to roll. There it goes. It moved real fast there. So that's what was holding us back. We had our proportional set too low. Apply. Let's go to 50. Apply that. Slammed it shut there. Let's put this at 20. It opens it up just a little bit. So we really kind of set this thing to the point where it doesn't even move. There it starts to move. We gave it a little bit of integral, and it started to move. So sometimes it'll get held up on you, and you're trying to figure out, well, why isn't it moving? So you want to play with these values. Usually you don't want these integral and the derivative to be 0, but very close to 0. But you can see it's moving fairly slow, and it's moving into a fully open position. Let's see if we can slow this down some. And this is, like I said, this is really an art. I mean, people that really know how to do this, they fully understand it. You know, they play with it. Now look how fast it's moving. It's moving real fast. Okay, so let's change that number to a lower number. .01. Apply. So it went back to 89, and it's slowly increasing again. It's going to go, what, to 90%. Isn't that the value we have? It's stuck at. Slowly increases. Let's change that to 34. But you get the idea. What this thing's doing is it's trying to make the process variable equal the set point. And obviously, you know, I'm manipulating the process variable here, but the reality of it is the process variable is like a level indicating transmitter or a flow indicating transmitter, and you're trying to control that variable, right? And the way you're controlling it is to control your control variable, and your control variable can be something that changes, like a modulating valve or a variable frequency drive. The next thing we need to talk about is those ISA symbols. Okay, the ISA symbols they're actually single line diagrams, if you will, and they have different types of lines, And you can go on Google and type in ISA symbols. You will get a ton of information on this. There's so much information on ISA symbols. There's even a society that deals with ISA symbols. And you can go to Wikipedia, you can look on Google, you can go to different sites and just study the different sites and try to understand these symbols. Because once you understand the ISA symbols, that means that you can talk to the chemical engineers of the world, or the mechanical engineers of the world, or the process engineers of the world. And you can read their language. And once you understand their language, you can take their language, the ISA symbols, and convert that into PLC code and design the control panel just off the flow diagram. The companies that I've always worked for, I used to do natural gas compression in one company. We used to build these large natural gas reciprocating machines, right? And we would drive big aerial compressors. And what we would do is we would create the flow diagram first, right? And once the flow diagram got approved by the client, then we took that flow diagram and converted that into the PLC and to the control panel design. And so my point is the flow diagram actually is the lead document. Once you get the flow diagram defined, then you can start building all the process and the actual skids and everything, because now you know what you're going to do. So again, you need to understand these lines, and if it's a solid line, it's a mechanical linkage. If it's a dashed line, it's an electrical signal. If it's a solid line with hashes through it like this, that's a pneumatic signal, that's an air line. And if you have a solid line with L's through it, that's a hydraulic line. So you need to know all these different lines. There's actually a lot more lines, and this is just a simplified example. There's one that has a line through it and has little circles on it, and that's like a data line, like Modbus communication or some type of serial communication to the DCS. Could be Data Highway Plus, ControlNet, Ethernet, Modbus RS-45, all kinds of different signals. So then when you look at these, remember what I said, it was an LIT-888. That's level indicating transmitter, right? So the first letter indicates the process. In general, the process that is being monitored by the instrument is indicated by the first letter. So it's F is flow, L is level, P is pressure, T is temperature, L is level, etc., etc. We went over level already here. I think that just about covers it. I can't think of any other off the top of my head. So here you got your second letter indicates the function of the instrument. Is it a FI, flow indicator? So you can actually see it's a flow and it indicates. So you can have an FI but without a T. So it's not you sometimes have a flow indicating transmitter. If it's FI, you don't care. It's a mechanical device. All it is you walk up to it, look at it, and say, oh, look, the flow is X. It's a little manual gauge in there. It's a digital gauge, but it doesn't go to any of your PLC or anything like that. If you have an FIT, then that's a flow indicating transmitter, and that would actually be a 4 to 20 milliamp signal back to you. FC is a flow controller. What is your flow controller? In this example, your flow controller is the PLC, right? But you can also have mechanical flow controllers, and those work very well if they're set up right. And then you got your LA, which is level alarm. LR, level recorder. PT, pressure transmitter. If I have a LT, that's a level transmitter. If I have a LIT, that's a level indicating transmitter. Temperature element, TE. The temperature element is the actual piece of metal, the thermal well that screws into the pipe, and then you've got your temperature element, your RTD, resistive temperature device, or your thermocouple embedded into that thermal well, and then the fluid that you're measuring the temperature of flows around that element, and obviously the temperature element has to be compatible with that fluid. You don't want it to stick a piece of stainless steel in acid or something, or put maybe some caustic material on something that would just eat it up. And obviously you want to also, if it's a high pressure line, you want to make sure all those fittings are rated for that high pressure line, not the subject here. But the temperature element actually screws into the pipe, and then your temperature transmitter actually screws onto that and slides into the temperature element. So in some cases, when the instrument is used for two purposes, or when the function of the instrument has to be more clearly specified, a third letter is used. For example, FIC is a flow indicating controller. F or LAH, level alarm high. LAL, level alarm low. Sometimes you'll see they'll draw a little symbol here, and they'll have an LIT, and then they'll have little letters off to the side of it, and they'll say HH, HLLL, and that means that they want that level indicating transmitter to alarm on a high level, a high level, a low level, or in a low level. So then they draw circles, okay, and then they attach these to the different areas. Now you see this dashed line right here? That dashed line means control room rack mounted high level alarm. Now, I've seen manufacturers that don't even understand this, or they don't do a real good job of it, and reality of it is it's kind of, you know, unless you've got your different company policies. And so what you do is you kind of find out what that company likes to see and how they like to see it, and they'll usually mark up your flow diagram accordingly and say, okay, we want all of our symbols to look this way, and you just follow it and move on down the road. At the end of the day, it all means the same thing. It doesn't really matter, and your customer's happy, so who cares, right? So in this true ISA symbols, these lines right here mean control room. And then here this solid, and this is an LAH, right? This is a level alarm high, high level alarm. LR is a level recorder. It's a solid line, right? So it's going to the control room. It's panel mounted as opposed to rack mounted. And then if it's just a circle level indicator, this is field or locally mounted level indicator. If it's an LIT, it's a field or locally mounted level indicating transmitter, and you know that that's a 4 to 20 milliamp signal coming back to your system. Okay, so here we have an entire process. The process is connected to this LT, which is a level transmitter. It happens to have a LI connected to it, a level indicator. So the operator can walk up to this level transmitter and know the actual level in the tank. These dashed lines are what again? Electrical, right? So if we go back up here, you see the dashed lines are electrical signals. And those signals are actually indicators, right? And they say, okay, I want a level alarm high. I want a level alarm low. I want a level controller. I want a level recorder. So this is all in the control room, and this is on the field side. Or this could be inside the PLC, right? You could display all this information and do all of this stuff in the PLC and display it on a operator interface terminal. Okay? So again, the instrument identification code here, you got your first letter and your succeeding letters. So A is for current, amps, right? It's alarm, it's readout, passive function. Okay, so you got C here. C is for control or contact. So the A here, if it's a first letter, it's current. If it's a second letter, it's alarm. If it's a C here, the succeeding letters is control or contact. E is element. F is flow rate. G is glass for readout. H is hand or manual if it's the first letter. And if it's the last modifier, it's a high, it indicates a high. The I, if it's the second letter here, it's the indicator, so like a LI, level indication. L is level. M is motorized, and then modifier median. P is pressure. R, the neutron flux, or the recorder if it's a second letter. So if it's a FR, it's a flow recorder. If it's an FRR, it's a flow recorder with a relay. S is a solenoid or switch. T is temperature, and a succeeding letter is transmit. So it's a transmitter, a 4 to 20 milliamp transmitter. Then you would have a level indicating transmitter, LIT. See how this works? And V is valve, W is well, like a thermal well, X is transducer, Y is compute, and Z is position. So if you have a ZCO, that's a common thing. That's a position closed, or a position ZCO, or sometimes you see an SYZ. It all depends on the different companies what they want that to mean. Okay. So now what we're going to do is we're going to draft some ladder logic using these IF symbols. So here we have a temperature element, flow transmitter, PIC, pressure indicating controller. Let's look it up. Pressure indicating control or pressure indicating contact. TR, temperature recorder. LAH, level alarm high. Okay, so what we're going to do is we're going to actually create a program from scratch. We're going to go through there and set up a level alarm, a level indicating transmitter, and we'll add some alarms to it. So we're going to go here and say File, go offline, File, New. Oh, we'll just take this one and modify this one. So let's go delete, delete. So now the first thing we need to do is we need to add an analog card. So we slide down to the I/O configuration, we right mouse click, new module, and we're going to add an analog card. Now you can see here it says analog, digital, communication, motion, all the different vendors, everything. Let's just start turning these off. And so when you turn these off, it leaves you with just the cards that are available for analog. Okay, so with all the different vendors. So we're going to grab an analog input card. Let's just slide through here. Let's just grab the top one, IF16. Say OK. Think about it. And then we'll give it a name if we want. You don't have to. We can change the slot. You can change what the data coming in. Is it a floating data point, differential mode? And that's the mode I like. I like to leave it in digital floating point differential mode. Revision is 1. And electronic keying, we went over that. We'll just say that we want a compatible module in here. Next. You can inhibit the module. You can, if a major fault on the controller, if connect fails when it while in run mode. And we went over that as well, in earlier programs. Next, next, and now this is where you actually scale it. So the first thing you want to do is say your input range. What is your transmitter, your level indicating transmitter? In this case, we want a 0 to 20 milliamp. You can do 0 to 5, 0 to 10, or minus 10 to 10 volts. So set that to 0 milliamps to 20 milliamps. And then your high signal, we'll go over here and say that's 20 milliamps. And your high engineering point, we'll say that it equals 100, because this is a level indicating transmitter we're talking about. We're trying to control the level of a tank. We're going to set this value to 4, and we're going to say that's 0%. The tank is empty. So we have a tank that goes from 100% to 0%. And then we have the RTS, which is that delayed time, and you can set up a delay on this and do a digital filter right here and actually delay how fast it responds, but we really don't care about that here. So we'll say next. The next thing we're going to do is we're going to set up the alarms, right? A high. Well, we want a high to be 95% of the tank's value. And when you hit 95 here, it automatically moves this high symbol up here. You can actually drag this around. And if you drag it around, it changes that value. And I believe if you hit hold the shift key down while you do it, it changes these in whole numbers, not in decimal point. So again, we'll just slide this on up to about 95%. And then we'll go down to the high and we'll drag it up to about 75%. We'll change the low to, let's see, how about 13%. And the low, we want to make sure we don't run that pump dry, so we're going to set her up at about 6%. We can put a dead band in there on these alarms. It's not really necessary if you've got a good level transmitter. If you click this, you'll disable all those alarms. You don't want to do that. So then you say next. Now here's calibration. And after messing with this some and playing with this calibration, it is not a good idea. If you get a card, which I did recently, get a card that the calibration was out, somebody had messed with it and then sent it to Alan Bradley, and then Alan Bradley, I guess, tried to fix it and send it to me, which was a big no-no because I'm an OEM. I only ship out brand new equipment, and you should only as well. I noticed that the equipment that we had in our facility was not high enough. The resolution was not high enough to make this work. So stay out of the calibration mode. Just leave it alone. If your card doesn't work properly, send it back to Alan Bradley. They'll send you a new one, and it'll be recalibrated. So you don't have to worry about this. I strongly recommend, unless you're a calibration lab, you need to stay out of this section, out of this area. So, and that's it. You're finished. So say finished. Now, we configured the card. It's in slot 0. And let's go to our main routine, which we're in. Let's add an input, or a rung. And what we're going to do is we're going to say we want to look at that value, right? So we're going to click that. We're going to go to our card, take a look at that one. So we got the channel faults, the actual fault conditions. Slide on down to, it gives us you under range, over range. So under range is if it's below 4 milliamps, it'll be an under range situation. So let's go ahead and click on that. If that's true, that'll close, and we want to go ahead and latch that in. We'll say LIT under range, and that'll be our deal there. And we'll just right mouse click on that and make that a tag. And then if that occurs, we want to go ahead and latch it in so we know what happened. And so we'll go ahead and put LIT under range. And then we want the operator or whoever to unlatch it, so we'll put a reset push button here. Okay, so now what we want to do is whenever the reset button is pushed, we don't have an analog card yet, so we could we have two choices. We could actually tie that to a panel view plus that actually understands what control tags are and understands a reset underscore PB, and you can actually import the tags to it and you can actually control it at that point. Or we can tie it to a input card. So we'll go ahead and tie it to an input card. We'll slide on down to the configuration and add a new module. We'll turn off our analog points. And we'll add an input card, an IB16. Okay. And let's say next, next, next. Not much you need to do there. Finish. We will add an output card too. And again, the reason I'm going through this again is because this is kind of like your final opportunity to see how an entire process would be looked at from the IS point of view all the way to the PLC input. So let's add an output card, and I really like those OB32s. They're okay as long as you turn on a relay with it, but I really like those OW16s. I like those relay isolated outputs, so we'll say okay to that. Finish. Okay, so now what we want to do is we want to actually tie this to an input. We're going to edit its properties, and what we're going to do is we're going to say alias. We alias it to that card. Controller scope, remember cards are actually controller scope, and we set our input is in slot 2, right? So we go slot 2, I, go to the data, click this little arrow, and it gives us the data. Remember, this is a 16 input card, right? So we'll say input 0 is the actual reset push button. That's what we're saying here. Say OK. Now you can see that whenever the reset push button is pressed exterior of the PLC, the input card will recognize it, and that's input 0, and that is now the reset button. So it's normally open button, and so if this occurs, this under latch, it turns on this bit, which latches itself on, and you've got yourself an alarm. Now let's go ahead and tie this to an output properties, and we'll just turn on one of those outputs. We'll do an alias again, and remember the output was slot 3, right? So we'll go to slot 3, data, and we'll make that one 0, and just hit enter. Okay, so now you've got that tied. You've got the level indicating transmitter under range tied to output 3. So we're going to go ahead and just add one more thing. We'll add this copy so that here we'll paste this right there. Double click on that. Let's go ahead and put over range as well, and then we'll just say, let's change this, and we'll say instead of under range, we'll just call this out of range. Out of range. So now, if it's above 4 milliamps, below 4 milliamps or over 20 milliamps, it's out of the range of the card. There's obviously a transmitter trouble. We'll alarm on that and turn on that output, 0. And we can continue this, and we will. Copy, paste, and let's pick another one. We'll just grab one alarm. You'll get the idea after this. A high. Let's delete this, and then let's grab this and say this is the high level indicator high. Let's make that tag. Let's go ahead and do an alias again. Controller scope. It's an output. Data. And we'll make that one 1. So now we've tied that internal tag, level indicator transmitter high, to the output card, which is in slot 3, and it is output 1. And we've got a reset button, and if we get a high alarm, that we could turn on a light or something like that. Okay, so now we've taken the level indicating transmitter and we've brought it in, and we've created 2 types of alarms. We've created a level alarm high, right, LAAHH, and we've also created a level out of range, if you will, right, a level indicating transmitter out of range. So you can see how this actually works and how to build this line of code. Now, I guess that's really at this point all we want to do, and I guess you could download this if you wanted to. Another thing we could do is well, you don't have to do scaling here because you've already done your scaling, right? In this particular card, you've scaled it by configuring it, so you've actually set it's 0 to 100%. And so you pretty much just set it up. You don't have to do any math or anything like that. You could, you don't even have to do greater or compare signals because of the alarm configurations, right? You got the alarm configuration. This control Logix PLC and ours Logix 5000 is almost like a little DCS because you've got these pre-made templates. It's not like the Ars Logix 500 where you actually have to create all this code and understand a little bit more about the raw values coming from the card itself. Okay, so we'll just recap. The main idea here is to understand that the ISA symbols found on flow diagrams or piping and instrumentation diagrams, that's the main idea. We want you to understand this, that these piping and flow diagrams are ISA symbols. And if you go to Google, and I strongly encourage you to, you can type in, ISA symbols. I think there's a company called PA Controls. Type in pacontrols.com. excellent source for instrumentation. That is a super website. These are the ways this is the way the ISA diagrams and the flow diagrams are the way programmers understand how to build a PLC control system. And by reading these diagrams, the PLC programmer understands how to program the PLC. So the key is the flow diagram, the piping instrumentation diagram is the lead document for you. And you need to learn how to read these documents, and once you understand how to read them, you can actually just create your code from there. And again, here if we had the following: a level indicating transmitter, LSHH, LAH, LAL, LSLL. Now here, S right here means shutdown. So we have level, shutdown, high, high, level alarm high, and level shutdown, low, low. If we have a level shutdown, we actually stop the process. We close the valve, we stop the pump, we close the modulating valve, we shut things down. This is you're going to overflow the tank, you're going to spill fluid all over the place. You don't want this to happen. If you have a level switch low, low, you're going to drain the tank. And if you drain the tank too low, you're going to starve the centrifugal pump of water and you're going to destroy it. It'll just destroy itself. If you have an alarm at LAH or an LAL, then you're getting to a situation where you might hit a high or an LL and you want everybody to know about it. So looking at an LIT, if they have HH, HL, and LL next to it, then you know you need at least one analog input and then 4 internally generated alarms and shutdowns. And those 4 internally generated alarms and shutdowns can be tied to I/O by using the alias like we just did, or simply using a screen like a panel view plus that can understand control Logix and read all these values. And then you can actually build. Also, the RSView Studio works like a champ, and we'll go over that later. Okay, so here we have, we actually went through this already, and I'm just kind of recapping here. We have configuration. We have a 1756 IF16 card. We've configured channel 7, 20 milliamps to 100, and 4 milliamps equals 0, so we've said its engineering units are 100%. Could be a 100-meter tank, right? Doesn't really matter. Input range is 0 to 20 milliamps, and we've got a little delay in there, and it's got a module filter of 3 dB, minus 3 dB. And then we went over that, the alarm configuration. We set the high to 90, the high to 90, the low to 30, and the low to 5. And we know we can drag these up and down, right? And we can change these values. And if we hold the shift key down and drag them, we get whole numbers, not 90.5 or whatever you want. And remember, that can't be checked right there, because if you check this, then this whole screen, you don't see any of these alarms. Okay? Okay. And then I showed you the tag monitor and how you can actually look at these values. You can see the high alarm is a Boolean value. The channel 0 data is a real value. And then here's a sample code. You can see I took the high alarm and I tied it to an alarm high, and it's got shutdown reset. Because remember, the LSHH, it was a shutdown. So here we have just a reset. It's just an alarm. It's a high value. It's an LAH. And then we had an LAL, right? It's an alarm as well. So it's just a reset button. We'll reset it. It doesn't shut the system down. And then we have a low. So technically this is a shutdown because it was an LLSL. So that shutdown reset should have been down here as well, because you don't want to be able to reset this unless the entire system is shut down. You've allowed the whole system to stop. So that's it. That's the end of the course. And what we've covered is in PLC number 3, Ars Logix 5000, we did the review for PLC number 2, homework. We covered JK flip-flops. We covered T flip-flops. We covered the compute, math, and move instructions. We covered the monitoring and editing tags, forcing and toggling bits. We did some basic troubleshooting on controllers. We configured the analog cards and set up a PID instruction. And again, that's an art, right? We introduced ISA symbols and how important they are to PLC programmers. and DCS programmers, you've got to learn how to read these ISA symbols. If you do nothing else, if you just want to be a programmer, you can study this PLC programming and disregard all the hardwire issues, although you will have to set up a PLC and snap in the modules and what have you. But if you don't want to design control panels and things of that nature, you need to learn, at a minimum, these ISA symbols. And then we did a lot of drafting of different logic. The next course in these series, PLC 4, up to this point, Ars Logix 500 and 5000, all we've covered is the basics. And when I say basic, I mean this is the basic information that Allen Bradley covers. So they don't go into a lot of detail. You know, there's a whole other realm to Ars Logix 5000 that we haven't even touched. Motion control, communications, redundancy issues, all kinds of different issues. And this advanced section can go on and on and on. It can go 4, 5, 6, 7, 8, 9, 10. In fact, I've noticed Allen Bradley has expanded on this Ars Logix series, and they're starting to open up their training courses, so it's getting better and better. So the Ars Logix PLC 4 class will be troubleshooting using the Ars Logix 5000 software, and that's more and more details about troubleshooting. And then we're going to create some networks, right? Set up some networks. We'll set up a Modbus communication link and show you what Modbus is and how it works and what RTU is and everything there. And then we'll go through converting Ars Logix 5 and 500 to Ars Logix 5000 code. You can go from 5 and 500 to 5000. You really can't go from 5000 back. We'll go through the trend charts. There's actually a trend function that you can use. And then we'll go in more detail on these emulators and simulators and play with those a little bit more as well. And when I go through the advanced section, I'm going to have to set up some hardware for that, and so that's a little bit more time consuming, and it's a little harder for you guys to set this up and play with it, but I'll do my best on that and try to make it as intuitive as possible. The Ars Logix 500 all series, 3 series are available. So if you've not taken this course or series of courses, you should seriously consider it. Ars Logix 5000 assumed that this material was covered. We skipped large sections of critical basic function, fundamental computing knowledge that was covered in Ars Logix 500 courses. And you can get the best deal if you go to the store, the eBay store, and do the, best offer or, something like that. And, click it until you get to the right number, and eventually it'll accept it. It'll actually auto-reject you a few times if you hit too low of a number. I appreciate it. Thank you very much for taking the time to listen to this. This was well over 4 hours here. So we appreciate that you have chosen PLC Training PLC courses to meet your PLC needs. And I want you to thank Allen Bradley and Rockwell Software for building such a nice program and hardware product line. These Allen Bradley products are excellent. Not only is their software excellent, but their hardware is excellent. And that's why they're such a good company to work with and to fully understand. Now, I'm not affiliated with Allen Bradley or anything like that, or Rockwell Software, but I can really appreciate their products. And like their AB 1200, that thing has a large mean time between failure, 250,000 plus hours. That thing is robust. It will last a long time. So if you're thinking about designing a product line, in manufacturing something, seriously consider these Allen Bradley products, because what I've done is I've taken the Allen Bradley Micrologix and I've put it in a simulated test, and I just sat there turning on large motor starters on and off trying to break this controller. It didn't break the controller. You know what it did? It broke the motor starter. So the motor starter's mean time between failure was much less than the controller's. And some processors or Micrologix PLC boards that people make, they don't understand how the hardware should work and how it should be optically isolated. And what happens is these inductive kickbacks of these big coils and noise and EMI problems and all these different things that can come into play destroy the hardware. And Allen Bradley has done an excellent job of protecting their equipment and making a nice controller. So it's a good team to be on. So thanks a lot, Alan Bradley. And if you have any problems, you can email me at vwedlick@gmail.com, and I'll be glad to help you. And best of luck. Take care.